Okay, so we were talking about chapter 15, and we started talking about really the common ion effect. And remember that really the sort of common ion effect is this idea when we have something like a weak acid or a weak base that when they are in solution with, say, a salt or some other sort of compound that has an ion that obviously is in common with, sort of what's floating around in there, it will really cause that equilibrium to basically kind of not break apart as much, or that weak acid not break apart as much. So, for example, we talked about the acetic acid, which again is a weak acid. And when it's in solution by itself, it obviously will break apart into its normal sort of ions, the acetate ion, and obviously some H plus. And that obviously is what's going on, in solution when it's in there by itself. Now, if we take our acetic acid and we also add in there maybe something like sodium acetate, which, so for example, here, we added some sodium acetate in there. So if we also threw in there our sodium acetate, which is a salt, and going to 100% break apart into sodium ions and acetate ions. And again, because this is basically a salt, it will strong electrolyte, it will 100% break apart. So the sodium acetate itself will not set up an equilibrium. It basically is just going to be a source of these ions that are going in there. So when we do add sort of that sodium acetate to that solution, which is just kind of visually what's going on, right? Visually what's going on is we essentially have our top equation happening. We got some acetic acid floating around in there. We have some acetate floating around in there. And we have obviously some H plus floating around in there. So by putting that sodium acetate in there, we're going to basically be dumping in here some more sodium ions and obviously some more acetate ions. And what that's essentially going to do is increase the amount of acetate ions that are in the solution. And based on Le Chatelier's principle, it would be like adding more of this guy. And that's going to cause the equilibrium to shift away from it, which means that the weak acid in this case, or when we talk about, say, a weak base as well, will basically stay together. And what that ultimately means about something, say, as involved like pH is because it's shifting away from the right-hand side in this case, we're not going to have as much free H plus in that solution that contains that common ion. And we would expect perhaps the pH to be higher because of that than it would be in just the acetic acid by itself. We also talked about in this situation, there's really two ways you can kind of solve sort of these problems. You can definitely do an ice table. So you could do an ice table. And the difference is with the ice table, for example, if we were doing the acetic acid ice table, the main difference and the important part where a lot of people screw up on is in the initial part. So you would have a number here. This guy would be 0, but you would have a number here again being supplied by the sodium acetate in this particular example. And you would go through your normal sort of ice table, just like you've done all the other ice tables, use the Ka value, solve for H plus or solve for X, which would be the H plus concentration. And you could go into your pH. So that's sort of one approach you could do with these sort of problems. Basically treat them just like a regular sort of Ka problem. The main difference though is you got to have that number on the right-hand side for the initial. Otherwise, again, you're not doing the common ion problem. You're really just doing the weak acid problem by itself. The other thing that we also see is because of this sort of situation that occurs with Le Chatelier's principle, basically pushing back on, say, the weak acid or weak base from breaking apart, what we know is that, relatively, in most cases, this change part is going to be pretty small. In a lot of cases, especially if we're starting with pretty good concentrations at each of these guys. And what that means is when we do reach equilibrium, for example, the number that we end up with and sort of the number that we started with will usually be pretty close to the same amount. Again, because of that very small amount that's going to break apart, we're not going to get a tremendous change that's going to occur. So in these sort of common ion problems, which are really buffer problems, which obviously we're going to talk more about today, and we talked a little bit about last time, there's an alternative approach that you can take to sort of solve these problems, and that's using the Henderson-Hasselbalch equation, and that is that the pH is equal to the pKa plus the log of the base over the acid. So that is the Henderson-Hasselbalch equation, and that should only really be used in this situation, which is again common ions, which is really buffer type problems, where the pKa value is minus the log of the Ka. So these two equations allow you really not to have to do the ice table. You could really just go right into there with the concentrations that are given to you, and it will give you the pH. We also talked about that there are sort of a Henderson-Hasselbalch equation for sort of basic situations that sometimes people use, and that is that the pOH is equal to the pKb plus the log, and again, it's opposite here, acid over base, where the pKb value would be minus the log of the Kb value. As I might have mentioned, I think last time, and I'll mention again here, we could absolutely use this equation, but and then sometimes people will use it for basic type situations. But really, a lot of times there's not a tremendous benefit for it because you're not usually in problems asked for what the pOH value is. Most of the time, you're asked for what the pH is. So in my opinion, you might as well just go straight into the Henderson-Hasselbalch equation because that does give you the pH at the end, which is ultimately what you're looking for in most problems that you do. But obviously, if you did this, you would need an additional step in most problems where, again, to find the pH, you would then have to take the 14 minus the pOH. And again, a nice relationship as well, just in case you want to use either one of those. The pKa plus the pKb does equal 14. So that's a kind of convenient way which you can kind of go from pKa value to pKb value if you needed either of those values. So Tim, are you asking when should we use this equation here or the
Yeah,
P?
because you said the most likely situation we'd use the Hasselbach equation, and I didn't hear you.
Yeah, so like I was saying, in most problems that you're asked for, you're usually asked for what the pH is in a lot of problems. Very rarely, in these
Sorry, I
type of
think you
problems.
said like it was for like acid base ones or buffer.
Yeah, so for sure, the Henderson-Hasselbalch equation, these are really used for what we were talking about, which are common ion problems. And common ion problems are essentially, as we'll talk about continually here in a few slides, are really buffer problems. So this is really should only be used in a sort of a buffer situation. And we're going to talk about what a buffer is in just a second, and you'll know sort of what it is. But really what a buffer is a common ion. So you got to have sort of that weak acid in either its conjugate base to start with, or you got to have, weak base and its conjugate acid. Both need to be in the solution, kind of like in this situation here, for you to use this equation. You can't use it if you don't have that situation. So it's definitely got to be a buffer situation to use the Henderson-Hasselbalch equation.
Thank
You're
you.
welcome. Other questions?
I have a question.
Yeah.
Is it safe to assume that the salt will always produce an acid and the CH3COOH will produce a conjugate base?
Yeah. So, salts, like we talked about in sort of that previous chapter, if you had something like acetate there to CH3COO minus, if it goes on and goes through hydrolysis, which it will because this comes from a weak acid, would act as a base and basically accept an H plus from water and make OH minus. While this is really just the dissociation of the weak acid. So there's always sort of that relationship that if you're starting with a weak acid, its salt part will be sort of the conjugate base, and vice versa. If you had a weak base, the partner that you typically would see in this sort of common ion effect would be its conjugate acid. If that answers your question.
For the Henderson equation, for the conjugate base over the acid, we would put the number of the salt over the number of the.
Yeah, so in the case, if we were going to kind of use it for this example, this equation, in this case, when we would look at, again, it would just be the acetic acid here that would set up the equilibrium. And since that's acetic acid, that's obviously going to be our acid part in the equation. And then its partner on the other side, in this case, would be the conjugate base, which would go up on top. And it would be opposite if we were dealing with sort of a weak base and a conjugate acid sort of situation. Obviously, the weak base would be the one on top in the formula, and then its conjugate acid would be the one on the bottom. So, for example, if you had, say, NH3 in with some NH4 plus, the NH3 would be the base, NH4 plus would be the acid in this particular case. You're welcome. Other questions? Okay. All right. So again, there's really two ways you can sort of solve these problems, and they both should give you really the same answer when it's all said and done. It's just your preference. So I can obviously save you time going to the Henderson-Hasselbalch equation. And as we've been talking about, again, the place where a lot of people do go sort of bad is they try to use that equation in every situation where they have two numbers. And again, it's a really narrow situation, as sort of the question Tim was asking. Again, it's about sort of the buffer situation, which is ultimately a common ion situation. All right, so I think where we left off was at this example here. So why don't you take a couple minutes here and see what you come up with. What is the pH of a solution? It contains 0.3 molar and 0.52 molar here, and the Ka value there is given to you for the acid. So see what you come up with, and we'll talk about it. All right, so a couple of things that, again, sometimes people run into trouble is they see these two things. They're not really sure what they're looking at per se. They're not sure, is this an acid? Is this a base, or whatever it may be? So what we have here is two things. We have HCOOH and HCOOK. I won't tell you the name of that just yet, so we can talk about how we can maybe figure it out. So, we definitely have a Ka value, which does mean that we should have a weak acid somewhere in the picture. So that does mean that one of these two guys should probably be the weak acid, right? And an acid, right, is pretty much something that can donate an H plus, right? So I could give away an H plus, which means in this particular case, it's going to be this guy here, which is the formic acid. This is going to be our acid. The other way that I know that is typically when an acid gives away its H plus, it makes a conjugate base on the other side. And the difference between the acid and the conjugate base is it lost an H plus, which means probably becomes something that's more negative, which if we look at this guy, this is basically a salt. That's why really the potassium is there. It's potassium formate, by the way. And this is the salt that's basically going to break apart into K plus and formate, which is this guy here. So now when you kind of break it apart, you can kind of hopefully see the relationship between these two. So typically speaking, if you're not sure, which one's which per se, the one that has maybe more H pluses, or at least one and more H pluses, is probably the acid. The guy that's got probably a kind of sodium, potassium, some type of spectator ion like that hanging out is probably going to be your base in that particular case. Any questions on that? So now that we know that, the other thing we want to know is, are these two things really related to each other? And they are. You can see that the difference really is one H plus difference, right? And that means basically we have a weak acid, and a conjugate base. And that again is basically two things that are related to each other. And as we'll talk about in just a second, that really is a buffer. And this is a common ion type situation. We know it's a common ion situation because this guy is a weak acid, which means if we take sort of the ice table approach, it will break apart into our H plus and our formate, and it will be the one that will set up that equilibrium. And initially here, we would have 0.3 molar. This guy would be 0. And again, because this is a common ion problem, really a buffer type problem, we do have some formate to start with. The formate is going to come from basically this guy here. That potassium formate is going to really be a source of formate that's happening. And that means that, as we talked about, it's important if you choose to do the ice table approach, that this part right here is not 0, that you do have a number there. Again, if you leave that guy at the end there 0, you're basically just doing a weak acid problem, which is not what we have here. The rest of the ice table would be minus x plus x plus x, and at equilibrium, 0.3 minus x, x, and x. Now, if you took this approach, you could then go obviously into your Ka. You could solve for x. X would equal the H plus concentration, and then you could go into your pH equation at that point. Now, if you could recognize that this is really a common ion problem or really a buffer problem, you could pretty much skip all of this and go right into the Henderson-Hasselbalch equation, where the pH is equal to the pKa plus the log of the base over the acid. Our pKa value here is minus the log of the Ka, which was given to us. So that's going to be minus the log of 1.7 times 10 to the minus 4. And it looks like maybe 3.77 on that, I think. So our pKa value is 3.77, which means we could go into our Henderson-Hasselbalch with 3.77 plus the log. And again, this is why it's important to understand which one's the acid and which one's the base here. And because of that, we would put obviously our base up on top, which would be our 0.52, and our acid on the bottom, which is 0.3. So 0.52 divided by 0.3, take the log of it, add it to 3.77, gonna give us a pH of 4.01, it looks like. And that would mean that this guy is obviously acidic. Now, again, if you took the ice table approach, it's perfectly fine to do it that way. You should also end up with a pH of 4.01. Any questions on any of those steps there? And again, it is your personal preference which way you kind of want to do it. You want to do the ice table, good to go that way if you want. You want to do the Henderson-Hasselbalch equation, it's good as well. Again, we did an example, I think the other day, where we kind of did it both ways, and we came up with the same answer. So again, I just caution you on the ice table approach. Can't tell you how many exam questions I've seen where this is incorrect. So don't forget that part of it. Any question on any of those steps where we got any of the numbers or anything like that? Okay. So what we're talking about here really is a common ion effect. And really, for the most part, people don't all the time call it common ion effect. It really is a buffer situation. And a buffer situation is always sort of a situation where we sort of have this common ion effect happening. So let's talk about really what a buffer is. As I find it here. There we go. So a buffer is a solution that basically has either a weak acid or a weak base and the salt of its conjugate acid or conjugate base. So a buffer is pretty much made up of a weak acid and the salt of its conjugate base. Or you can make a buffer with a weak base and the salt of its conjugate acid. So you may be asking, what does the salt part mean? The salt part means what we were just talking about when we were looking at the one we just did. This was our weak acid. And the salt was this guy. This is the salt of its conjugate base. what makes it a salt is just what we were just talking about. It basically has that K plus and the minus to balance out the charge. So it's got that spectator ion. Now they both need to be in sort of the beaker to begin with in order for a buffer to work. Now, what is a buffer, or what does it actually do? Well, a buffer is able to resist big changes in the pH, even if you decide to add more acid or base to it. So if you just have a buffer solution sitting there and you take some acid and you add it to the buffer solution, it will be able to pretty much maintain its pH. Will it go up or down if you add acid or base to it? It will, but it will not go tremendously up or down. So, for example, if your solution was a pH of 7 to start with, and you add acid, it won't go from 7 to 1. So it won't have a giant jump. It may go from 7 to 6 point something, but it won't be giant in terms of the jumps in the pH. The other important thing about a buffer that people truly sometimes misunderstand is a buffer does not mean that the solution is neutral. So a buffer does not mean that the solution is a pH of 7. You absolutely could have a buffer at a pH of 7, just like you could have a buffer at a pH of 1, buffer at a pH of 11 or 12 or 10. You could actually make a buffer at any pH you want. So you could really have a buffer at any pH. What it means in a buffer is, for example, if we started with a solution that was a buffer and it had a pH of 5, and if I add some acid to it, maybe it goes down to like 4.90 or something like that. It doesn't go tremendously far down. Or maybe if I added base to that buffer, maybe it goes up to 5.1 or something like that. But it will not jump from like 5 all the way to 12 if you add a base to it, or it will go from 5 all the way down. So what a buffer means is whatever pH it's made at, and again, you can make it at any pH you want, it basically is able to maintain that pH without going really crazy. And really the reason it's able to do that is because both of those things are in there to begin with. So if we were to make a buffer, for example, like out of the problem we just did, what it means is we would have floating around in that solution some of our acid, and we would also have some of our base floating around there, and we also have some spectator ion floating around. But to begin with, our buffer would have a base part, and our buffer would contain an acid part to begin with. And that's critical for how a buffer is really able to sort of maintain that pH. And it's critical that both of those things are in there to allow it to handle when you decide to add some acid or base to it. So let's talk about, sort of how it sort of functions. So let me go back a couple of pages here so I got somewhere to write. Okay, so let's say, let's just say we started with water, right? And water is not a buffer. And let's just say we had some water and we decide to add a strong acid to it, like HCl, right? So we went and grabbed a bottle of hydrochloric acid and we added it basically to a beaker of water. When we add that hydrochloric acid to water, we know because it's a strong acid, it is going to 100% break apart into H plus and Cl minus. So by adding that HCl to water, which is not a buffer, it is going to have no problem 100% breaking apart into these guys. And because it 100% breaks apart into these guys, we have now just produced in our little beaker of water, we just produced a lot of free H pluses floating around. And what we just did is essentially increase the concentration of H plus. And as you remember, hopefully from pH, if we increase that concentration of H plus, that means that the pH is going to go way down, right? The amount of H plus went up high. pH is going to go down. And in this case, maybe our water started at a pH of 6. It might go down to a pH of 1 or something like that, because again, we generated a lot of free H plus from the hydrochloric acid that was added. Now, let's say we took our water and did the same thing and we added something like a strong base to it, like sodium hydroxide. Same idea when we add basically sodium hydroxide to water, again, water not being a buffer. That sodium hydroxide is going to 100% break apart into sodium ions and hydroxide ions. And just like our strong acid, again, 100% is going to break apart. What did we essentially do there in the beaker? Well, what we essentially did is we didn't add a ton of H plus, but we added now a ton of OH minus that's freely floating in that solution, a lot of it. And as you also would remember, hopefully, as the concentration of OH minus increases, the concentration of H plus will decrease, right? Because they are tied together. And by extension, the pH will go up, right? Because we got a lot of free OH minus. And again, that's based off of the idea of the pH is equal to minus the log of the H plus concentration. So by having a lot of H plus in the first case, we're going to see that pH go down. And by having more OH minus, the H plus concentration goes down and the pH will go up. So this is what happens when we add, again, a acid or a base to something that's not a buffer like water. And in the case of the bottom there, again, maybe our water started at a pH of 6. Maybe it jumps at that point to a pH of 12 or something like that. A pretty big jump in pH. Any questions on that so far? Okay, so then let's talk about what happens if we take these same two things, but we add it to something that actually is a buffer. So let's use the most common buffer that everybody loves, which is, we'll go with acetic acid and sodium acetate. So we have an acetic acid and a sodium acetate buffer. Get rid of that there. And this is definitely a buffer in this situation. And again, how do I know it's a buffer? Again, this is our weak acid. And the acetate part here would be the conjugate base. So that is a weak acid. And what makes it the salt of its conjugate base is the part where it says sodium acetate. So that is a weak acid and the salt of its conjugate base. So let us take our same HCl that we added to water, and let's see what happens when we add HCl, again, not to a buffer of water, our beaker of water, but a beaker of this buffer. And what we're going to have in this buffer, again, is our acetic acid floating around in there. It's actually going to set up that equilibrium. We're actually going to have some acetate floating around as well because of the sodium acetate. And by default, we'll have some sodium ions. Again, sodium really just a spectator ion, not participating. It's just kind of hanging out to balance out charge. But the two main parts that we have here when we look at this sort of buffer is we have the acetic acid, which essentially is the acid part of the buffer. We have our acetate, which is the base part of the buffer. So when I dump my HCl in there, I am dumping obviously an acid. So it is going to react with the base part of the buffer, right? Because they're called acid-base reactions. They're not called acid-acid reactions or, base-base reactions. So they're called acid-base reactions. So what's going to happen when I dump my HCl into here, it is actually going to do a chemical reaction with the acetate part that's in the solution. And it's going to basically react with the sodium acetate, which again is the base part of our solution. And when it reacts with that, excuse me, we will pretty much get an acid-base reaction or a double displacement reaction, however you want to think about it. Positive, negative guy, positive, negative guy. Two positive guys going to switch partners. It is going to produce acetic acid in that double displacement move. And it's going to produce some sodium chloride in this case, right? And again, this guy and this guy are going to basically switch partners. Now, what we just produced now in the actual solution, if we kind of look at our solution and see what we have in there at this particular point, we just produced some acetic acid, which was already in there to begin with, right? So that's obviously not going to screw anything up in terms of the pH. We also produced some sodium chloride, which would put some more sodium ions in there, which sodium is a neutral salt, not going to mess the pH up. And we produced some chloride ions, also a neutral salt, not going to mess the pH up here. So when we look at what we produce as a result of this reaction, by the way, you always do this. You always produce the other part of the buffer. So that always happens. So that's helpful when you're trying to figure out what's happening in terms of the equation. When you add an acid or base to the buffer, it will react with one part of the buffer, but it will produce the other part of the buffer. And we produce this neutral salt. Now, the more important thing is actually what we do not see present when we look at this. So when we look at the product side here in this reaction, we do not see any free H plus being formed. And if you just to remind you, if we go back, we see a lot of H plus formed when we add that to a non-buffer solution. We produce a ton of H. But over here, when we add it to our buffer, we have no free H plus formed. So what does that really mean? Well, if we didn't form any more free H plus, that means the concentration of H plus has remained relatively constant. And that means that the amount of H plus that was there before, which there is some H plus just from the original guy that was in there, the acetic acid, the H plus remains relatively constant. That means that the pH will also remain relatively constant as well. And ultimately what that means is when we add our acid to our buffer, instead of producing a lot of free H plus in this case, the H plus actually gets tied up and makes acetic acid, and it makes that sodium acetate or sodium chloride in this case. And again, by not making any more free H plus that wasn't kind of there to begin with, we are basically going to keep that concentration constant and the pH will remain constant. Will we see a little bit of a decrease in pH? We will, because we are going to produce a little H plus because we are producing more acetic acid as well, which is going to produce a little bit of H plus, but it's a weak acid, which means it's not going to produce a lot of free H plus. So that's why if we actually have a pH meter in this buffer, we would see the pH go down a little, but it wouldn't jump tremendously. So for example, this buffer starts somewhere around a pH of 4.74. It would not go all the way down to a pH of 1 if you added the acid to it. You know, again, it would stay somewhere in that 4.7-ish range or something like that. Any questions on what happens when we add it to we add acid to a buffer? So let's talk about what happens when we add a base to a buffer. So we'll use the same buffer here. So we'll have our same acetic acid buffer and our sodium acetate buffer. And again, this is really our acid part of the buffer. This is our base part of the buffer. And just like before, if we sort of draw our little kind of beaker, just like before, we essentially have our acetic acid that's in there. That's obviously missing a 0 there. Setting up our acetate that's in there. Also has got a little bit of H plus to begin with in there. And again, we have some sodium ions basically floating around. And that's just from our normal kind of starting point. So if we then take our sodium hydroxide and we add it to it, obviously sodium hydroxide is a base. So when it reacts with our buffer, it's going to react with the acid part, which is acetic acid. And this is going to do a normal acid-base reaction. And basically, we're going to make water and a salt, which in this case is sodium acetate. So we do see a couple of things here. We do see the same thing as we saw above. We used some of the acetic acid, but we made the other part of the buffer. We also made some water, which is really not going to have a big effect on the pH. So if we just kind of dump in there, the stuff that we added that kind of came in when we added our sodium hydroxide as a result of this, again, we're going to basically have water, which is obviously not going to affect the pH. We'll have some more sodium ions from the sodium acetate, and we'll also have some acetate ions, right? Which are there to begin with, to start with. So again, we did not produce anything that's going to really affect the pH. And just like previously above, it's actually what we do not see here that's kind of important. What we do not see is, in this case, we do not see any free OH minus being produced. And again, just to remind you, if we look back to what happened when we added our sodium hydroxide in water, we produced a ton of free OH minus. But here, when it reacts with our buffer, we don't produce any more really free OH minus. And the importance of that is that the concentration of OH minus remains relatively constant. Thus, because H plus is related to that, the H plus concentration remains relatively constant. And finally, what that means is the pH will also remain relatively constant. And again, the idea here is a very simple one. It's all really based off of our pH equation, which is this guy, right? So what affects the pH is as this concentration changes, the pH changes a lot, right? Which means that in both of these cases, what we're able to do is keep the concentration of H plus relatively constant. And by default, what that's able to do is keep the pH relatively constant. Same idea here. And the reason why, again, I say relatively constant is if you had a pH meter in that buffer and you added some sodium hydroxide to it, you would see the pH go up. But again, it will not go up tremendously. So you won't see a giant jump in pH. Again, a very modest sort of increase in pH, but not tremendous jumps in pH. Question on fundamentally how a buffer actually works. Any questions on that?
So the buffer solution, what's the interaction there? Because it seems like they share the same anion, right?
Mm-hmm.
Do they reach equilibrium? Because obviously, if they did a double displacement, they would be the same things. Like nothing would change, I suppose. But
yeah, so what's essentially happening is when you make a buffer, for example, there's a couple of different ways you can actually make a buffer. One way is basically you like go to the shelf, for example, in this one, you grab the acetic acid, you dump it in, you grab some sodium acetate and you dump it in together, it mixes up. And just like we talked about, what's essentially going to happen is it's really just the acetic acid in this case that will set up that equilibrium, right? The sodium acetate that you would put in there is still a strong electrolyte, so it's going to break apart, but the acetic acid will produce some sodium acetate. And by you adding some more sodium acetate in there, you're just kind of beefing up the amount, this kind of starting amount that's present in that solution of the acetate part, and you still have the acetic acid part. So when you dump either the HCl in there or the sodium hydroxide in there, you're going to get basically a chemical reaction. And through those chemical reactions, what you're doing is you're kind of in the beaker, if you will, or wherever you're dumping it in, you're essentially regenerating some of the buffer, right? In the first case there, when we added the HCl, we're regenerating some more acetic acid in that case, right? As we can see here. And we're kind of rebuilding that, but we are using a little bit of the sodium acetate part that was present in there. Some of it will be regenerated a little bit, but we are going to use some of it up. And the same idea with the sodium hydroxide, when we add it, we're going to use up some of the acetic acid, but we are sort of regenerating more of the sodium acetate. So in the case of that, what we're essentially doing, even when we're adding acid or base to, say, this buffer, and again, it is the acetic acid is really the only thing in there that's going to sort of maintain this equilibrium setup here. We're basically, in certain cases, adding more of this guy. In certain cases, we're adding more of this guy. And that's ultimately how a buffer is able to sort of maintain its pH over a good period of time, especially if you make it sort of correctly with the right amount of concentrations of everybody. And that's why it's able to keep maintaining that pH, even if you kind of add more and more and more either acid or base to it. Answer your question, I hope.
Yeah. So the salt is just sitting there disassociated, the Na.
Yeah. So really, so again, you can kind of think about this, and again, in real life, they're not like sitting, in a line like an equation right in the beaker or anything like that, but essentially what's happening is the weak acid or even the weak base is really the one that's going to set up this guy. And if we just dump the acetic acid in there by itself, right? And we go, okay, well, we have a buffer because obviously it made this, right? It's not going to be able to make enough of this just by itself to really allow the buffer to work effectively. So that's why we sort of has to add that sodium acetate in there to beef up the amount of acetate that's present in this beaker to start with. So we have the right amount of concentration that is actually able to resist changes in pH. So you can't just make a buffer, for example, if sort of that's your question. Like if I just dump acetic acid in there, it's going to make some acetate. So I should be good in terms of like a buffer working correctly. And you won't really have the right concentration of each of those in that solution to really allow it to function correctly as a buffer. And so that's why we typically will add the extra sort of conjugate base, in this case, to the solution to sort of beef it up. And ultimately what we're doing, again, it's like they're not going to really come out in an equation or anything like that, but we're really just getting a solution that has a good amount of acetic acid in there, which is really the acid part of the buffer. And by adding that sodium acetate to there, we're really getting a good amount of the base part of the buffer to be present, sort of at the start of the reaction when we add more, say, sodium hydroxide or hydrochloric acid to it. Other questions?
Okay, thanks.
You're welcome. Other questions on how it functions? So that's actually a good question, because it does lead to sort of an idea of, there is sometimes referred to sort of as a buffer capacity, or how effective a buffer is. So typically when we do make a buffer, as we just saw with those reactions and we just talked about, is, if we have a buffer, what we try to do is a lot of times make the acid part of the buffer kind of equal to the base part. And that's sort of what I was just talking about, that, when we're starting with a buffer, we do want a good amount of both of those guys really floating around in the solution. And if we get a good amount floating around the solution, what we do see is as we add acid, to the buffer, it's going to react with the base part of the buffer, but it is going to make the acid part. So what we will see in a very exaggerated drawing here is we will see the acid part get bigger, but the base part, will get smaller in a sense. If this is again still the buffer here. And if we add base to the buffer, the base that we add, like sodium hydroxide, will react with the acid part, but it will make the base part of the buffer. And again, a little bit over exaggerated on the drawing here, but we'll make some more of the base part of the buffer. And obviously the acid part of the buffer will get smaller. So there is a limit to how effective a buffer can be. So for example, if you, didn't maybe read the instructions or just kept adding acid, what's going to happen? Well, if you kept adding acid to this, eventually you will continue to, I'm sorry, not adding acid, adding base, since we're going this way. So if we add more base to this guy, we'll essentially continue to eat up the acid part of the buffer until at some point, there's no acid part left. All we essentially will have left is the base part of the buffer. So what's going to happen at that point, once we sort of use up all the acid part? Well, once you continuously add your, say, sodium hydroxide, you're now going to add just a bunch of OH minuses at this point. And at this point, we would see a big jump in pH because we basically blew right through the buffer part of it. It's not able to handle all of that. Same thing would happen if we went the other way. If we continuously just added acid to this buffer and didn't pay attention, we'll continuously use up the base part. We'll continuously use up the base part. And at some point, we'll blow right through the base part of it. All we will have left is the acid part of the buffer. And we will start making a lot more H+. And it would be at this point, either side there, it would no longer be able to act as a buffer. And at that point, we would definitely see a big jump in the pH because we basically blew right through the buffer part of it. So, I mean, that's one way, you could kind of blow through a buffer. The molarity of your buffer and the molarity of the acid or base that you're adding to your buffer is really important. Again, same idea. Let's just say you have this buffer to begin with, and the instructions called for you to grab the 1 molar hydrochloric acid, and you grabbed like the 18 molar hydrochloric acid and you dumped it in there. You're just going to blow right through the base part. And at that point, you'll just be adding a lot of free H+, and you will see a big jump in pH. So there's really two important things when you think about making a buffer is what should the concentration of the actual buffer be? And, what is the concentration of, say, the solutions you're going to use in the buffer? Because if you kind of choose those things incorrectly, you could end up with a situation where, you will blow right through your buffer. It will not be able to handle it. So it's really important, what you're adding to it in terms of their concentrations, and it's important what you're adding in terms of the buffer itself. Because ultimately, when we look at a buffer like the guy up here on top, there's only a certain number of moles available to react. Same thing here. There's only really a certain number of moles of that guy to react. And if you add way too much of your acid or base to it, you could blow right through it. So there is a capacity for buffers. And you usually do want to kind of think about, how it's going to be used and the concentration of everybody to make sure that the buffer that you're making would work effectively. Any questions on that? So what is a buffer? So obviously a buffer, as we talked about, has that acid part, it has that base part, it has a weak acid and its conjugate base, or a weak base and its conjugate acid. And that really is what we've been talking about since the beginning of this chapter. That really is a common ion problem, which means buffers are exactly where you should use the Henderson-Hasselbalch equation. And again, really the only place you should use the Henderson-Hasselbalch equation is a buffer. You should, again, not use it if it is not a buffer situation, because it will be wrong. So you want to use this only in these buffer situations, which are really common ion situations. And as I mentioned earlier, as we talked about earlier, you could use this guy for acidic, basic, neutral type buffers. And I would recommend, as I said earlier, that to use this one, again, because, most of the time you're asked for the pH. So if you use that other one, which is the POH, you're going to have to still figure out the pH. So might as well go right into this guy. Our alternative, if you still want to, and you do not want to use the Henderson-Hasselbalch equation, you could still use an ice table to solve these type of problems. Any questions on buffers, how they work, how they function, why they function? And obviously, as I mentioned, this is specifically where you should be using that Henderson-Hasselbalch equation. Okay, let's see here. So here's just a picture that sort of illustrates that. Again, in a non-buffer solution, when we add some hydrochloric acid like we see here, because of that increase in the amount of H+, we could see that the pH goes from 7, for example, all the way down to 2-ish, 1 and change, by adding just a little bit of hydrochloric acid, as opposed to in a buffer situation. Excuse me. In a buffer situation, it's able to maintain its pH by, again, preventing the formation of either H+ or OH-, depending obviously on what you're adding. So by keeping those guys' concentrations relatively constant, that allows you to basically keep the pH relatively constant. And again, as I said, if you had a pH meter in there, you would definitely see the pH go up or down. But again, we won't see a tremendously giant jump in the pH up or down. And by the way, as you hopefully know, if you add the H+, it should go down the pH, right? OH-, the pH should go up, right? All right. Any questions on any of that? So take a second here and look at each of these and decide whether or not each of these could be a buffer or system or not. Take a second. We'll talk about which ones are, which ones are not. You need those two things, right? You need the weak acid or weak base and its conjugate acid or conjugate base. So really, what does that mean? It's really the same relationship we talked about with Bronsted-Lowry. We need at least two things that are related to each other by only a difference of an H+. So if we look at A, we have HF and KF. Again, the K here is potassium. That's going to be a salt, which basically means we have K+ and F-. So we basically have these two guys, and they are related to each other. The only difference is one H+. The other thing you need to figure out is this guy weak or strong? And hopefully you know this guy is a weak acid. That means that A would be a buffer, right? So that could be a buffer solution made out of that. If we look at B, same idea. We got KBr and HBr. KBr, again, a salt, going to break apart into K+ and Br-. So again, we do have two things here that are related to each other. So you might be thinking it is a buffer, but one important part is this is actually HBr, and this is a strong acid. And a strong acid cannot be a buffer. So this cannot be a buffer. So why can you not make a buffer out of a strong acid or a strong base? Well, the reason when we talk about buffers being a weak acid or a weak base and not a strong acid or a strong base, I want to put that. You cannot have a buffer. How do we do it that way? No, not make. We cannot have a buffer out of a strong acid or a strong base. And that's because let's take something like HBr, right? When we throw HBr into a solution, because this is a strong acid, it's going to 100% break apart into H plus and Br minus. So in this solution, what we're going to have floating around with to start with is H plus and Br minus. We'd also have some K plus and Br minus. So when we're looking at the solution, we do have the base part of the buffer, but we're missing a very critical part. We do not have the acid part of the buffer. Again, because the HBr will not set an equilibrium because it's a strong acid, so it's going to 100% break apart. So it lacks that acid part like we would in an HF solution. In an HF solution, we would have HF floating around, we would have F minus floating around, we would have that K plus floating around and F minus. So in a weak acid, because it sets up an equilibrium, it keeps the acid part in the solution, just like a weak base would keep the weak base part in the solution. So you cannot have a buffer that is made up of a strong acid or strong base, again, because they really will not set up the equilibrium. It will not allow that part to stay in solution to help act as a buffer that's needed. Not to confuse things, you can actually make a buffer out of a strong acid and strong base, but the buffer itself cannot be made up of a strong acid and a strong base. So two kind of things there, and we'll see an example of that I think a little bit coming up, but you technically can really make a buffer from a strong acid or strong base, but when the buffer is actually made and done, the strong acid or strong base is gone, it's not there anymore. So what you're left with is a buffer, but you definitely cannot have a buffer made up solely of a strong acid or a strong base. Because of that, it will not set up an equilibrium. You will be lacking either the acid part of the buffer or the base part of the buffer. Any questions on that? All right, so we have some sodium carbonate and sodium hydrogen carbonate here. And again, we basically have CO3 2 minus. We get rid of all the sodiums. We have HCO3 minus. Again, these two things are related to each other. That comes from carbonic acid. So this guy would be a buffer, part C. So it looks like B is the only one that will not be a buffer in this particular case. Any questions on that there? Okay. So let's try some calculations here to see what we do with buffer calculations. So part A is calculate the pH of a buffer that contains 1 molar acetic acid and 1 molar sodium acetate. Part B, we'll talk about together in just a second. So for now, just work on part A. The Ka value for acetic acid there is on the bottom. So take a minute or two and calculate what is the pH of this buffer when we make it here with 1 molar acetic acid and 1 molar sodium acetate. So a couple of things. They were nice enough to say that this is a buffer, so that's a super big hint here. If they didn't tell you it was a buffer, again, you could look at this, which is acetic acid. This is sodium acetate, so they obviously are related to each other, and it would be a buffer. And what that really means is, you know, probably the best approach here would be to use the Henderson-Hasselbalch equation, because you could go right into that. So if you chose to do that, they did give you the Ka value here. So the pKa value would be minus the log of the Ka. That would be minus the log of 1.8 times 10 to the minus 5. And that's going to give you a pKa value of 4.74. We then can, for part A here, go right into that equation. That's going to give us 4.74 plus the log of the base, which again, this would be our base. If you're not sure, this is the Ka value for acetic acid, and the name kind of implies that it's an acid, right? And in this case, that is the log of 1/1. And if you're familiar with that, that's the log of 0, which basically means that we would open up in this case with a pH of 4.74 for this buffer. Any questions on how I got to that number there? And again, because I recognize that it's a buffer, I went right into the Henderson-Hasselbalch equation. If you wanted to do an ice table would be just like what we've done before. It would look something like this if you chose this approach, which is perfectly fine if you want to do it. Initially, this would be 1, this would be 0, and the important part here, we would have a 1 for the acetate on our initial coming from here. Change would be minus x, plus x, plus x, 1 minus x, x, and 1 plus x. This obviously would go into our Ka, which would give you x times 1 plus x divided by 1 minus x. And I won't continue the rest of it, but you basically solve for x, which would be your H plus, and then you could go into your pH, and it should end you right there as well. So any questions on sort of the alternative approach that you would take? Okay. So again, that is the sort of the 2 ways that you could calculate the pH of a buffer to start with. But what we're going to talk about in part B, and we'll go through it here together, but in part B, what we're going to do is we're actually now going to take our buffer that's maybe in a beaker, and we're going to add some hydrochloric acid to it. And we want to see what happens really to the pH once we add that hydrochloric acid to it. So a couple important aspects for this chapter, and especially when we're talking here with buffers and when we add sort of more solution to it, one important aspect of it is when we add solutions together, as we've talked about before, the molarity changes, but what stays the same is the moles, because remember, molarity is moles of solute per liter of solution. So when we add like HCl to a buffer, we're changing the bottom part here, and the molarity changes, but the top part remains the same. So one really critical aspect when you're doing problems that involve a situation where you add something to another solution, and you might need to do an ice table, is you need to do the ice tables in moles, not molarity. So whenever you have a situation that you're going to add one solution to the next, which happens with buffers, also happens with the next big topic we're going to talk about, which is titrations, right? In titrations, you're constantly adding volume, so the molarity is constantly changing. You want to always do it in terms of moles. So we're going to then, in this case, add some hydrochloric acid to our buffer, and it's going to be the same buffer we were just using. So those values there were, we have a 1 molar of each of those, and we're adding 0.1 molar HCl. 0.1 molar HCl is being added, and we have 1 molar of this guy and 1 molar of this guy. And specifically for part B, it says keep the volumes constant at 1 liter. Not always the case, but we'll assume here that everything's just going to be 1 liter. That way we can kind of do the math relatively easy. So if everything's 1 liter, that means we would take 1 liter times that gives us 0.1 moles of HCl added. Obviously, if we take 1 liter times this guy, we would have 1 moles of that guy, and 1 liter times this guy would give us 1 mole. Again, not always the case that the volume will be held constant, but we will in this particular problem. Also really important, again, is that recognition of when you look at a buffer, what you are looking at. Again, this is acetic acid, so that's obviously our acid part. This is our sodium acetate, which is our base part of the buffer. So when I add hydrochloric acid to it, that is an acid, which means it should react with the base part. So we are going to need a reaction that's going to occur, and that's going to be HCl plus the base part of the buffer, which is our sodium acetate. And when that reacts here, we will end up with, much like we talked about, we will end up with some acetic acid, and we will end up with some sodium chloride. So we do need to do an ice table here to see what happened to our buffer once we added our HCl. So again, we want to do this in moles here because we're adding. So we have 0.1 moles. This is going to be 1 mole. And again, important where people screw up on is, again, you do need to have the 1 mole on this side. If you make this side 0, that is not a buffer. So you got to make sure you have that on that side as well. It's very, very common. People kind of do that. The other difference is here, normally when we get to the change part, we use X because we're not really sure what the change is. But in this particular case, we know what the change should be. Because this is a buffer, we know that pretty much when I add my HCl to it, the buffer should use up all my HCl. So instead of using an X here, we will actually use the number because we know that all of this HCl that we added to this buffer should get used up. So the change here would be minus 0.1, minus 0.1, and plus 0.1 on this side. That means when I reach equilibrium at this point, I have no moles of the HCl left, which is what I would expect to happen because it all should be used up. I should end up with 0.9 moles of my sodium acetate, and I should end up with 1.1 moles of my acetic acid in this case. Why did I not do anything over here with the sodium chloride? Well, as I mentioned before, sometimes it's best not to put numbers somewhere where you might want to use them. The reason I'm not going to use it is this guy is a neutral salt. It's going to have no effect on the pH, so I'm not going to put any numbers here and try to use them where I shouldn't. Any questions first off on the ice table? And again, we do need to do the ice table to allow us to know really how, the purpose of the ice table is to figure out how the buffer is changing by doing this little reaction that occurs. Now, once we do this guy in moles, it is very good practice at this point to convert these moles back into molarity. So that's going to give us 0.9 molar since we're assuming 1 liter. So at this point, once you do that first ice table, you should take the total volume and convert it back into molarity. So again, this would be the total volume. In this particular case, we're keeping it constant. So that's why it hasn't changed. It will change in a non-constant situation. Any questions on that? All right. So at this point, sometimes people will go, I'm not really sure what I should be doing, but your ice table actually can help you. If you look at the ice table, when we reach equilibrium, we have some sodium acetate left. We also have some acetic acid left. And hopefully you should still recognize those two things as still a buffer, which is what we would assume it to be. And what that means is we have 2 options here to get to our pH. The easier option would be to go into our Henderson-Hasselbalch equation at this point. So our pKa value is the same as part A since it's the same acetic acid. So that's still 4.74 plus the log. And it's important here again to recognize which one's your base and which one's your acid. Again, this guy is our base. The acetic acid is our acid. So we would put the 0.9 divided by the 1.1. And if we do all that good stuff here, 0.9 divided by 1.1, take the log of it, add it 4.74. Looks like we end up with a 4.65 as our pH. First off, any questions on that? Now, does it make sense based on where we started? Well, we started with a buffer on the last page here that had a pH of 4.74. We added some acid to it. It went from a pH of 4.74 to a pH of 4.65. Not a tremendous difference in pH, but more importantly as well, it went in the right direction. And what I mean by that is we added acid, which means we would expect the pH to go down. So it went from 4.74 to 4.65. It went in the right direction. If you did this calculation, you ended up with a pH of 4.9 or 5, you're going in the wrong direction because you're adding acid in this particular case. Any questions on that there? Okay. I know we're a little bit over. Just to finish the thought here before we stop, a reminder as well that, again, this is one approach as to how you could figure out the pH at this point. If you wanted to do an ice table instead, just to kind of, again, show you what it would look like, it would be our acetic acid breaking apart. And again, here, the important part is you would take your equilibrium values, and those would be your initial values. So you would have 1.1 here, and this would be molar at this point. This would be 0.9 molar. This would be 0. You would do your minus X plus X plus X, 1.1 minus X, 0.9 plus X and X. And just like we talked about before, that would go into your Ka. You would solve for X. X would equal the H plus concentration, and then you could go into your pH, and you pretty much should get the same guy as you did here. So again, it is really your preference, whichever way you want to do it. Obviously, if you could recognize it as a buffer, common ion type problem, going into the Henderson-Hasselbalch can be a little bit easier. Also, maybe a little less room for calculation error, but you could still always go into the ice table if you wanted to. And again, because it is a buffer, this is the important part here, that you do, just the top guy there, that you do have that initial amount there of the 0.9. Any questions on any part of that calculation?
Professor?
Is the second ice table that you did, is that just to double check that you got the right answer? And
Yeah. No, you don't have to double check with the ice table. It's just an alternative approach to getting the pH rather than using the Henderson-Hasselbalch. If you use the Henderson-Hasselbalch, you're good to go. It's probably the right one as long as you punch it in correctly. But some people don't want to use the Henderson-Hasselbalch because they're afraid they may use it in the wrong situation. So you can, again, just kind of go to the ice table if you want to go that way and do it. You could do one or the other. I wouldn't recommend doing both, to be honest with you. So you could choose whichever way you want to do it.
okay, thank you.
You're welcome. There's another question? Or...
No, you just answered my question.
Okay. Any other questions on any of this? Yeah. So again, you know, Henderson-Hasselbalch, probably the easier approach, probably less room for error. But again, if you're unsure you should be using it, or, you know, can't remember it for some reason, you could always, like I said, go into the ice table, and again, and maybe a little bit longer of a calculation, maybe a little bit more room for error. But you know, you can definitely do it. So ice table you could always use. Henderson-Hasselbalch you could only use if it's a buffer situation. So that's an important distinction between those two. Other questions? Okay. All right. So we'll stop here. And I think what we'll do is we're going to be doing an experiment. We're doing 6 today, which I think is buffers. And we have one more example. So I think we'll finish the next example and kind of wrap up the buffer talk, and then we'll talk about the experiment.